So far, we've talked about respondent conditioning kind of in a vacuum. We discussed situations involving just two stimuli, the US and the CS, and we saw how learning happens when those repeatedly show up together, right? Especially when the CS is predictive of the US showing up right afterward. That said, a lot of real-world situations involve more stimuli than just a single US and a single CS. So let's add one layer of complexity here so you can see at least kind of how we would deal with that situation, even though we won't go too deep down this particular rabbit hole. So after you've done respondent conditioning, the CS-US pairing, and you've created a CS that elicits a conditioned response, then you can go a step further and you can actually pair that CS up with a different neutral stimulus. And often the new stimulus may start to produce a CR, its own conditioned response, even though it's never actually been paired with the US. So this is called higher order conditioning, where you're sort of chaining together a series of associations, at the very bottom of which is the actual unconditioned stimulus, the thing that had the power to elicit a response naturally, right? The reflex at the bottom of this. But you can build sort of layers of associations with associations with associations. That's higher order conditioning. So you could, for example, start with a US paired with what we might call our CS1, our first conditioned stimulus that we want to train. You just pair those up over and over again until the CS1 starts to elicit a conditioned response. That would be our normal respondent conditioning. There's nothing higher order or fancy here, right? But we might just call it first order conditioning. But now that CS1 elicits a response, we might pair CS1 up with some brand new stimulus, something that starts neutral but is going to become conditioned. So we might call it CS2, the second conditioned stimulus here. If we keep pairing CS1 and CS2 over and over and over and over, eventually CS2 may start eliciting its own conditioned response. That would be second order conditioning, where you pair a CS1 with a CS2 rather than a US with a CS. But you can go even further. So third order conditioning would be to take that CS2 that now elicits a response and pair CS2 up with some new stimulus, some neutral stimulus. We'll call it CS3, right? It'll become our third conditioned stimulus. Pair those up over and over again, and eventually CS3 will elicit a conditioned response. Theoretically, you could keep going, but in general, there is a limit to how much associative power can be passed through a chain like this. After all, if you think about it, CS3 has never been paired with the US, nor has CS2. It never gets matched up with the unconditioned stimulus, the thing that we naturally have a reaction to. So it's kind of amazing that they could be eliciting responses related to that US just through the intermediate steps of other associations. At some point, that connection is just going to get stretched too thin to cause much of a response. But we can at least get a couple steps. Second order and third order conditioning are pretty common. That said, second order conditioning is probably the most common, and it's really easy to demonstrate in the laboratory and see how this happens. So for example, with a rat in a little testing chamber, you might first play a tone right before a shock over and over again. So tone, shock, you pair tone plus shock, tone plus shock, tone plus shock, until the rat starts to have a reaction, a conditioned response, like freezing, to the tone itself. That would then be the tone is now a conditioned stimulus. We'll call it CS1 just to keep track of it, right? Then what you do is you'll pair that tone, pair CS1 with, let's say, red light. So the red light comes on right before the tone plays. Now there's no shocking involved at this point, though we know the rat already freezes to the tone. So you can do this over and over again, light plus tone, light plus tone, light plus tone, over and over. Pretty soon the rat will start freezing when the red light comes on, even if no tone shows up. And that's weird and kind of cool because the rat has never had any sort of naturally aversive thing show up after the red light comes on. Just something that it had learned to dislike sometimes showed up after the red light. In other words, the tone it had learned to dislike. That's enough for the rat to freeze to the light. That said, the rat is going to freeze less to the light than it does to the tone because of that further distance from the original painful US, the unconditioned stimulus. And also, the more you do this higher order conditioning, the more it actually starts to kind of erase itself unless you keep doing the lower order conditioning as well. Think of it this way, because every trial of the light plus tone is also a trial where the tone is happening without the shock. That means it's an extinction trial for the first order conditioning at the same time that it's strengthening the second order conditioning. So that's why you can't keep doing this sort of higher order chaining, higher order connecting over and over and over and get up to the fifth level conditioning or something, unless you're constantly reinforcing those earlier pairings, the lower order conditioning as well. Okay, so I know rats don't represent your daily experience, so I tried to come up with a more real-life example, which might be something like this. Let's say you've got your traditional first-order respondent conditioning. Maybe your girlfriend happens to wear a vanilla perfume, so you start to associate the lovely unconditioned stimulus of smooches with the smell of vanilla. So those smooches naturally give you some warm fuzzies, right, as an unconditioned response, but soon the vanilla smell itself is enough to give you warm fuzzies as a conditioned response to the smell. But where does higher order conditioning come into play? Well, let's say just by chance you happen to smell vanilla every time you walk past a bakery on your way to work. Over and over and over again, day after day, as you walk past this particular bakery, see the bakery sign, you smell vanilla. Now remember, you've been programmed to have positive associations with vanilla based on that first order conditioning, the earlier conditioning. So soon you might find yourself getting the warm fuzzies, a conditioned reaction, just from walking past the bakery, even at night when no vanilla smell is coming out of it, right? Even when there's no vanilla smell, you might start to have pleasant associations with the bakery just because it's associated with vanilla in your past experience, and vanilla in your past experience before that is associated with smooching. So the bakery comes to be a sort of pleasant, conditioned stimulus all by itself, even though it's never been paired with your girlfriend or her smooches. That would be the idea of higher order conditioning. This stuff happens to us all the time in our day-to-day experience. Our brain just makes these associations. And in fact, higher order conditioning shows up a lot when we analyze like marketing campaigns. For example, the really famous branding that Coca-Cola did to associate their brand with Christmas time. First, they started with an already existing association that was common, at least in the Western market, which is that Christmas had positive associations. So Christmas imagery kind of elicits happiness. This isn't something that's innate. This is not a reflex, right? It's learned. So we're dealing already here with a CS eliciting a CR. So we could call Christmas imagery CS1, right? Now, meanwhile, Coca-Cola was facing a dilemma around this time, which is that people didn't have any strong positive associations with their brand. Indeed, there was not really a big distinction between Coke and Pepsi at the time the way there is now. It was actually much more rare for anyone to have a strong preference between the two. They're just colas, right? Not a big difference. There wasn't a lot of branding yet. Then they started this brilliant ad campaign. So they repeatedly paired Coca-Cola with Christmas imagery. Their brand, which was previously a neutral stimulus, started to be associated with Christmas. In other words, it became a CS2. And eventually, with enough of this pairing over and over and over again, when people had seen these ads enough, Coke actually found that there was a big increase in positive feelings about their brand. So the CS2, just the brand itself, had come to elicit positive feelings by associating itself with something that already had positive associations. And that is higher order conditioning. For now, we're not going to go any deeper into higher order conditioning stuff, but I just wanted to bring up a couple other effects that happen in respondent conditioning when we, like this, involve more stimuli than just a single US and a single CS. So let's talk about a couple different effects, not higher order conditioning, but that are kind of similar because they have multiple stimuli involved. So first, there's something we notice, a phenomenon called overshadowing. So if we pair, let's say, two neutral stimuli, we'll call them CS1 and CS2. But if we can consistently pair these two things with the US over and over, they keep coming before the US shows up, then the most salient conditioned stimulus of those two, the one that stands out the most, will come to elicit the conditioned response much more than the less salient, the less noticeable conditioned stimulus. So, for example, let's say you turn on a really loud tone and a faint light right before you shock a rat. So the shock is the US, right? That's going to naturally cause a response when you shock the rat. But we have sort of a couple of warning signals now. A loud tone as one warning signal and a little faint light as another warning signal. Well, the loud tone will come to elicit a conditioned response much better, much stronger, and much quicker. But on the other hand, let's say instead your warnings, your two warning signals were a quiet tone and a bright flashing light prior to the shock showing up, prior to the US. In that case, the light will come to elicit a conditioned response much better, much stronger, much quicker. So whichever conditioned stimulus, whichever the kind of predictive or warning stimuli is most salient to that creature, whichever stands out the most from the environment, will get the strongest learning. That's the basic idea of overshadowing. So even though both of our stimuli, the light and the tone, might get 100 pairings with the US, they might show up 100 times right before the shock. Maybe even in both cases, 100 times showing up exactly 500 milliseconds before the shock. You might think that would lead to equal learning, but it doesn't, right? Because of overshadowing. So for example, in a laboratory, the most basic procedure to show overshadowing would be something like have a training phase where both of those CSs, both of those conditioned stimuli, get paired with the US repeatedly, like light and tone, both coming on before the shock. Then what you do is a test phase where you try the tone alone and see how much CR you get, and one where you try the light alone and see how much CR you get, how much conditioned response you get from each of those. They're rarely going to elicit the conditioned response equally, despite having the same number of pairings with the US. One usually overshadows the other. So it tells us that respondent conditioning is not just about the number of pairings. Since both stimuli got the same number of pairings here, but one is learned better. There's something else going on in our learning, and in this case, it seems to be the salience of the stimuli involved that's playing some additional role. So the type of stimulus that we're pairing up with our US does make a difference to how much learning we get. There's actually an alternate procedure that's commonly used to demonstrate overshadowing. So there you might instead just compare two groups. You might start with two groups, like let's say two groups of rats, for example. Group 1 gets light and tone, both paired with the shock, for let's say 100 trials. Group 2 gets just one of the stimuli, like only the tone, but again paired with the shock, let's say 100 times. At this point, for both groups, the tone is paired with the shock 100 times. Both groups have heard tone come on, then shock 100 times. So you might think they would have equally bad associations with that tone, that they would have a freezing reaction to the tone equally. So we check this by doing a test phase. For each group, we'll just check how much conditioned response we get when we play the tone by itself, with no shock and no light also. If what we find is group 2 showing more freezing, and group 1 isn't as scared of the tone, then that suggests the light was overshadowing the tone for them. It was kind of drawing off some of the limited associative power that the shock had to give, so there was less learning left over for the tone. Again, the amount of overshadowing will be determined by how salient one stimulus is relative to the other, or to the others if you had 3 stimuli showing up at the same time prior to the shock, or 4 stimuli, or 5, right? Even just the background, like the wallpaper in the room or things like that, could kind of be a stimulus that's present prior to the shock. But some will stand out more, will draw our attention more. That means they're more salient. And while this stuff might sound needlessly complicated, it's actually how the real world works all day long. So when you sit in the sushi restaurant for the first time, you might also be hearing the jazz music they're playing, but you're also seeing a variety of other visual stimuli, perhaps a lot of green if that's their color scheme in the restaurant, and maybe you're hearing the chef speaking Japanese, and who knows what other stimuli are all going on together. So if you then get sick after visiting this sushi restaurant and you throw up, you don't necessarily find jazz music and the color green and the sound of Japanese very aversive. You don't start to dislike those things, but sushi might develop a pretty significant conditioned response. So some stimuli connect more easily to the unconditioned stimulus, the thing that shows up afterwards. In any situation, when we're exposed to one stimulus, we're also generally exposed to a bunch of other, at least background stimuli, even if it's just the room we're in, or the time of day it is, or how caffeinated we happen to be right now, or what we're wearing, or a million other things. But thankfully, most of those things get treated as kind of background stimuli, not very important, not very salient, and they don't form a strong association. while other things, and especially like new and novel stimuli, they more easily form associations and come to elicit conditioned responses. Okay, the other effect I wanted to bring up that's kind of like overshadowing because it involves two CSs is called blocking. Basically, after you pair a CS with a US, just a single CS with a US, you do that normal training, that normal acquisition. Turns out it becomes harder for us to later train some other CSs with that same US, with that same unconditioned stimulus. To see what I mean, imagine an experiment like this. Here's a common setup in a laboratory. Step one would be to pair something neutral, like a light, right? A certain light, that'll be our conditioned stimulus one. Pair that up with a shock repeatedly over and over again. Obviously, this is normal respondent conditioning. The light will start to cause a CR, right? If we're pairing it with a shock, it's going to start making them dislike the light. The light is scary. They might freeze to the light. But for this experiment, for our blocking experiment, let's now go further. Let's add an additional step. So in step 2, in the next phase of this experiment, we might pair the light that they saw before and also a tone. So we're going to play both. We're going to turn on the light and the tone at the same time. Then the shock comes on. And we'll do this pairing over and over again. So it's light and tone, then shock. Light and tone, then shock. Light and tone, then shock. And do that for a while. Right? Now, step 3 will be our test phase. Here we want to test the tone by itself. So they already learned to dislike the light, because that came before the shock, but now afterward we're also throwing the tone in there as a sort of additional warning for the shock, right? An additional signal that predicts the shock is about to happen. So in step 3 in this test phase, let's just see how much the tone does, how much conditioned response we get from the tone by itself. And what's weird is we don't usually find a conditioned response to the tone, or not much of one, maybe a really weak one. And the question is why? Basically, what we think is going on is the prior learning about the light blocked learning of the tone. Now, why does that happen? What's going on here with blocking? Maybe because the first CS, the light, is already a really great predictor of the unconditioned stimulus, a really great predictor of when you're going to get shocked. Then the other CS, the new one, the tone, is kind of redundant. It adds no new information. So some people like to give the analogy of hiring someone. Imagine you run an investment firm, a stock investment firm, and you've hired Anne, who turns out to be the perfect stock analyst. She can always pick a winner. Okay. If Bob then comes along 1 week after you hired Anne and he can also pick stocks perfectly, I mean, that's cool, good for Bob, but who cares? He's redundant, right? He doesn't give your firm any additional predictive power because Anne is already such a good predictor of the market. Similar kind of idea with the blocking effect. If the light gives you really great predictive power already, it tells you when the shock is going to happen, then adding the tone, even if it's also a good predictor of the shock, doesn't really add any new information or help you in any way. So the brain kind of discounts it. It doesn't pay as much attention. But one downside of this way of explaining overshadowing and blocking and why they occur is that the way I've explained it here seems to kind of require some hypothetical cognitive variables, some sort of mental constructs, things like expectations and predictions and what the organism already knows, so knowledge. And using that stuff to explain learning, it isn't ideal for the framework we're coming at as behavior analysts. The whole idea with behavior analysis is that we should be able to explain behavior without resorting to hypothetical mental variables. We should be able to explain behavior as a natural science just based on the things we can observe, the behavior and the stimuli themselves. So in the video after this one, the final video on respondent conditioning, we'll actually learn about an alternative, maybe a better way to think of these things that'll explain blocking and overshadowing and stuff like that. So a comprehensive model that'll help predict all the stuff we know about respondent conditioning. Overshadowing, blocking, all of that, but purely with observable behavior. None of these hypothetical cognitive constructs needed. It's called the Rescorla-Wagner model because it was originally proposed by Rescorla and Wagner. But before we get into that video, before we get into that bit of theory, I wanted to bring up one more applied example for respondent conditioning where it'll help us understand something that happens, in this case, with drug use. So let's start with this. In a lab, for example, if you inject adrenaline into someone or something, an animal or a human, the heart rate increases. there's no learning involved there, right? This is a simple reflexive response as part of the built-in biology that we have. So let's say, just to do this in controlled circumstances, I'll do it on a lab rat. So let's say I do this with a rat and I repeat the procedure in the same little testing chamber day after day. In some sense, that testing chamber is a stimulus that happens to be present when the adrenaline is injected. So we've actually got a CS-US pairing happening over and over just by the rat being in the same testing chamber each day. Each day, the rat first ends up in the testing chamber, the CS, then shortly afterward gets injected, that's the US, over and over and over again. So eventually, when you put the rat in the testing chamber, you get a conditioned response, even before you inject any adrenaline, or even if you don't inject adrenaline that day, you get a conditioned response. That shows us that the chamber itself has become a CS. Now remember, the conditioned response, for the thing we've trained for the CS, the conditioned response, that behavior is not always the same behavior as the unconditioned response. So when we inject adrenaline, right, the heart rate goes up, but simply putting the rat in the chamber doesn't necessarily increase its heart rate in the same way. It doesn't necessarily have the same behavioral consequences. In fact, the CS going into the chamber turns out it comes to produce a decrease in heart rate as its conditioned response. We might ask why. Well, because that's going to help the body maintain homeostasis, right? Balance against the upcoming expected adrenaline injection that the brain, predicts is coming based on our past learning. So this is what we're talking about when we talk about something like tolerance to drugs. It can be explained with learning principles. The conditioned stimulus of the testing chamber actually is what evokes a lower heart rate that then weakens the overall effects of the drug. Thus, it takes more adrenaline injected to get the same heart rate spike that we used to get. That's drug tolerance. And note here that the importance of the drug context, the CS, in enabling tolerance. Now, why do I bring up this artificial example with lab rats, right? Because the same idea actually helps us understand something that kills a lot of people in real life drug use situations. So for example, heroin users, over repeated use, they'll often develop a tolerance, and as they're developing this tolerance, they're often using the drug in a particular context. So that context being like the usual paraphernalia, the usual room that they're in, the usual addict friends that they're around, things like that are a context that often shows up with the unconditioned stimulus, the heroin itself. That means eventually the CS, that context, simply being in the room, being around those people and objects, comes to elicit a CR of its own. Just like our rat example with adrenaline, the conditioned response to being in the heroin environment, the heroin context, the conditioned response to that is actually the opposite of the effect of heroin. It's the body's way of preparing for the upcoming heroin that it expects, trying to counteract it to maintain homeostasis. So, when the user is in the usual context, the CS and the US are both present, the CS helps cancel out the unconditioned response. Thus, an extreme dose of heroin doesn't have as extreme an effect as it would on a newbie with no learning and no conditioned stimulus to help elicit that counteractive conditioned response. That's the whole idea of tolerance. That's someone who's built tolerance to heroin, right? It takes a bigger dose to have as big of an effect because of what your body is doing prior to the injection based on the context. But here is where things can go terribly wrong for people. What happens when someone uses, in a new context? Well, the heroin is still going to elicit an unconditioned response. The heroin still does its thing. But now there's no conditioned response for the body to compensate in the opposite direction since there's no conditioned stimulus present to cue that up. Which means if the unconditioned stimulus of heroin is a really big dose, the unconditioned response might be deadly big. Someone who built tolerance doesn't necessarily have the same tolerance in all situations or contexts, and not realizing that has actually led to a lot of overdoses and deaths. Indeed, the same effect can be shown with heroin in lab rats They had these lab rats where they built up a tolerance to heroin in 2 groups of rats. There's also a third control group. They didn't build up tolerance yet. And then they injected these rats in the same room they'd been injected in the same room they'd built up the tolerance in, and a third of those died. So here's the group that got the big, huge injection of heroin, a large injection of heroin, in the same room that they were used to getting their normal, smaller doses, right? Then there's this second group of rats. They injected these rats in a different room than where they'd built up the tolerance. And what happens? Almost 2/3 of them died. So twice as many die. And then, of course, the control group of rats, those who hadn't built up any tolerance at all, they all died regardless of the room they were in. But that middle bar is the important one for human application. By lacking the conditioned stimulus, by lacking the usual context, there was no conditioned response to compensate and balance out the effect of that much heroin. In other words, despite both of these 2 groups having built up the same tolerance to the drug, their tolerance didn't kick in this middle group because there wasn't the respondent conditioning cue present. There wasn't the CS. All right. We will end the video there, and then I've got one more video for respondent conditioning. In the final video, I'll introduce that Rescorla-Wagner model that I mentioned earlier that tries to tie all of this respondent conditioning stuff together into a neat, elegant package to explain things.